Hello and welcome to the channel. This time our goal is to find the last three digits of 2 to the power of 1000. In fact, two approaches demonstrated here can be applied to any problem of this type. A typical common calculator can hardly help here, as it will either fail or show few most significant digits, while we are actually after the least significant digits. There are several big integer classes for programming languages like Java, C#, Perl, and Scala. Third-party libraries exist for some other languages like C++. A language like Python will be an excellent choice for someone who deals with large numbers on a regular basis, as it treats all integers as big integers. And finally, there is a big number calculator online with certain limitations. A link to it you will find under this video. So, let's start. Using the first method, we increment the power and find a repeated sequence of digits. Here I 2 times used a common calculator, but it can be easily done without it. So a number we deal with is 2 to the power of 1000, name it Z for short. Using power multiplication rule, it can be represented as 2 to the power of 4 and then to the power of 250. 2 to the power of 4 is 16. 6 squared is 36, of course, and it ends with 6. Any further multiplication by 6 will also give 6 at the end. Therefore, any power of 6 ends with 6, and any power of a number ending with 6, like 16 in our case, also ends with 6. So the last digit of Z is 6. And we move to the second last, or penultimate digit. Let an be the second last digit of 16 to the power of n. Then 16 to the power of n has some starting digits, and the penultimate digit is an, and the last digit we know is 6. Using Pn for the number composed by the starting digits, we can write the expression for 16 to the power of n. 16 to the power of n is 100 Pn plus 10 an plus 6. We want to express an plus 1 in terms of an. To do that, we need an expression for 16 to the power of n plus 1. So we multiply by 16 and distribute. We want to get separately a term with factor 100, a term with factor 10, and a free term. For that purpose, we split 160 an as 100 an and 60 an. Similarly, we split 96 as 90 plus 6. And we group them, and we get the following expression for 16 to the power of n plus 1. The first term with factor 100 ends with 2 zeros, so it does not affect the second last digit. What really defines the penultimate digit is the second term. We see that the second last digit of 16 to the power of n plus 1 is actually the last digit of 6an plus 9. So we can write that an plus 1 is the last digit of 6an plus 9. In mathematical terms, it can be written using mod. But if you are unfamiliar with that, never mind, as long as you know what it is all about. So we have the recursive formula for an, and we can find a1 given that 16 to the power of 1 is just 16, which has second last digit 1. So a1 is 1, and to find a2 we use the recursive formula. 6 times 1 plus 9 is 15, the last digit is 5, so a2 is 5. Now for a3, 6 times 5 plus 9 is 39, so a3 is 9. And a4 is the last digit of 63, which is 3, and a5 is the last digit of 27, which is 7. Then 6 times 7 plus 9 is 51, so a6 is 1. And this is the same as a1. According to the recursive formula, any value of an depends only on the preceding value, which means that starting from a6, the sequence of digits will be repeated. a7 will repeat a2, a8 will repeat a3, and so on. So we have a sequence of 5 repeating digits and can find an for any n. In order to do that, we divide n by 5 and get the remainder. If the remainder r is positive, then an equals ar. But we don't have a0. Therefore, if n is a factor of 5, we just take a5, which is also a factor of 5. Since a5 is 7, all a's for a factor of 5 will be 7. So we found that the last two digits of 16 to the power of 5m are 7 and 6 for any natural m, meaning a positive integer. In particular, for m equals 50, we get 16 to the power of 250 ends with 76, which is number that we are targeting. And we move on to the third last digit. So we know that 16 to the power of 5n, which can be written as 16 to the power of 5 and then to the power of m, ends with 7 and 6. Let's use for brevity letter s for 16 to the power of 5. So we can write that s to the power of m ends with 7 and 6. S is a 7-digit number, which I obtained using a common calculator, but what we effectively use is just the third last digit, digit 5. In order to obtain it, it will be enough to operate only with 3 last digits of each number. So if you do it on paper, you can stop once the third last digit is evaluated and proceed to the next operation. Once the third last digit is known, we can write s equals 1000m plus 576. Here we apply the approach similar to the one used to find the second last digit. Bn is the third last digit of s to the power of n. We already know that b1 is 5, and s to the power of n has bn as the third last digit, followed by 7 and 6. Using qn for the number formed by the starting digits, we can write s to the power of n equals 1000 qn plus 100 bn plus 76. And we multiply by s and distribute. There is no need to explore the first term with factor 1000, as it ends with 3 zeros and does not affect the third last digit. However, the second term is important, so we substitute s there. Before we can proceed, I will move the last expression to the top and wipe the obsolete lines. So we multiply the terms. The terms with factor 1000 aren't really important, so we just group them. However, the last term has to be distributed. Here I again use the calculator to find the product of 576 times 76. However, this time we also need only the third last digit. And again, some terms have to be splitted in order to collect separately thousands and hundreds. Then we group similar terms, getting quite a long expression where we actually need only the second term, a factor of 100. And we found the recursive formula for bn. So we can wipe the lines that are no longer needed. And again, we are looking for the repeated sequence of digits. We found previously that b1 is 5, so we just copy that. For b2, we use the recursive formula. 6 times 5 plus 7 is 37, so b2 is 7. Then 6 times 7 plus 7 is 49, so b3 is 9. And b4 is the last digit of 61, which is 1. Then we get 13 ending with 3 for B5. Then 3 times 6 plus 7 is 25, so B6 is 5. And B6 repeats B1. And again we have a repeated sequence of 5 digits. We are looking for the power of 50, which is again a multiple of 5. And B for a multiple of 5 equals B5, which is 3. Which means that s to the power of 5n ends with 3, 7, 6 for any natural n. In particular, taking n equals 10, we get that the 3 last digits of s to the power of 50, which is our target number z, are 3, 7, 6. The problem is solved, but there is something more to that. So let's explore s to the power of 5n by substituting 16 to the power of 5 for s. Again, we use power multiplication rule, and we can also replace 16 with 2 to the power of 4. Using again power multiplication rule, we get that s to the power of 5n equals 2 to the power of 100n. So we can write that the last 3 digits of 2 to the power of 100n are 3, 7, and 6 for any natural n. This of course applies to an infinite range of numbers, not just to 1000. We are moving to the second method, which is quicker but requires some special knowledge like modular arithmetic and Euler's totient theorem. This is an extension of the technique presented at Math Stack Exchange page. The link to the page will be placed under the video. So here is Euler's totient theorem, also called Euler-Fermat theorem, which is an extension of Little Fermat theorem. If a and m are co-prime positive integers, then a to the power of 5 of m is congruent to 1 modulo m. This notation means that a to the power of 5 of m minus 1 is divisible by m. Phi of m, named totient of m or Euler's phi function, is a number of positive integers no more than m and co-prime with m. Normally the totient is not calculated directly because there is a convenient formula to compute it. We only need a special case when a equals 2 and m equals 125, which is 5 to the power of 3. When m is a power of a prime number, which is what we have now, the totient can be computed using this simple formula. In our case, phi of 125 equals 5 to the power of 3 minus 5 to the power of 2, which is 100. So Euler's totient theorem gives 2 to the power of 100 is congruent to 1 modulo 125. According to the properties of the modular arithmetic, we can raise the last equation to the power of n, where n is a natural number. And we get 2 to the power of 100n is congruent to 1 modulo 125. This is the only place where we use Euler's totient theorem, so we can wipe out all the previous lines and move on. For module 8, we don't need Euler's totient theorem. Instead, we just write 2 to the power of 100n equals 8 times 2 to the power of 100n minus 3. Since n is a natural number, the power for the last term is no less than 97 and is positive. Therefore, the last term is a whole number, so 2 to the power of 100n is divisible by 8. In other terms, 2 to the power of 100n is congruent to 0 modulo 8. While doing that, I haven't forgotten about the goal, which is to find the last 3 digits of 2 to the power of 100n. So let x be the number formed by the last 3 digits. Firstly, x is a non-negative number which must be less than 1000, otherwise it would have more than 3 digits. Secondly, 2 to the power of 100n minus x has a 0 at the end, therefore is a multiple of 1000. This means that x is congruent to 2 to the power of 100n modular 1000. But 1000 is 125 times 8. And since 1000 is a multiple of both of them, we can replace modulo 1000 with modulo 125 and modulo 8. From the last two equations and equations above, we can conclude that x is congruent to 1 modulo 125 and at the same time congruent to 0 modulo 8. Now we can wipe out everything apart from the shaded stuff. Here are our three relations that survived the demolition. If we find a value satisfying to all these relations and show that there is no other value like that, then x must be equal to this value. The second relation means that x equals 120a plus 1, where a is an integer. The third relation can be written as x equals 8b, where b is also an integer. We can merge the last two equations and write that 125a plus 1 equals 8b, and both equal to x, where a and b are integers. This is a Diophantine equation that can be solved in a standard way. But since we only need non-negative values of x less than 1000, we can just try all possible values of a. Firstly, we observe that a must be in the range from 0 to 7. As for a negative a, the value of x will be negative, while with a 8 or more, the value of x will be over 1000, which also should not happen. Secondly, a must be an odd number, because if a is even, then x is odd and is not divisible by 8. This leaves the following values for a: 1, 3, 5, and 7. The following table lists all possible values of a with corresponding values of x. We see that 376 is the only value of x divisible by 8. Therefore, x must be equal to 376. Consequently, the last three digits of 2 to the power of 100n are 3, 7, and 6 for any natural n. In particular, 2 to the power of 1000 also ends with 3, 7, and 6. Using this approach, it can be proven that 9 is the fourth last digit of 2 to the power of 500n that adds another digit for 2 to the power of 1000. Also, 2 to the power of 2500n ends with 09376, while for 2 to the power of 12500n we can name 6 last digits: 109376. The last equation in particular applies to the power of 2 of 10 to the power of k, where k is 5 or more, such as 100,000, 1 million, etc. Here is the moment of truth, the big number calculator. 2 to the power of 1000 is a 302-digit number. To our big relief, it really ends with 9376. 2 to the power of 2000 has 603 digits and also ends with 9376. 2 to the power of 10,000 has 3011 digits and 5 predicted digits at the end. The biggest power of 2 the calculator could give is 99,999. It has 30,103 digits. The last digits are different because this is not a multiple of 100. For the power of 100,000, the calculator failed. Nevertheless, we know that the last digits are 109376. Finally, we reached the end.